Hello students, welcome back. Let's go back to section 4. We completed one type of variation of parameter problem, which is also called reduction of order problem. Suppose that we have one solution of a homogeneous linear ODE and we are looking for another solution. We begin with a linear combination. Y of 2 is C times Y1. From here, you can change this C into parameter and then take the derivative using the product rule and so on, and do your computation and simplify. You're going to get a reduced equation. What am I talking about? Here's a concrete example. Begin with, this is y1, begin with u times y1, and here are the derivatives. Plug everything back into the original equation and simplify. And as usual, the u term will completely drop out. Why? That's going to be a homework problem. Consequently, you're going to end up with a reduced equation. The second order dropping down to a first order. For this reason, this kind of method is called reduction of order. So that's an example of variation of parameter. We completed this kind of problem. Reduction of order, and then you can find out u, and then consequently you get y2 as u times y1. Got it? So we get the general solution, c1y1 plus c2y2. It's an example of variation of parameter, but this is more typically called reduction of order. More people call variation of parameter as the second example, as a matter of fact, but me, they're basically the same thing deep down, so I prefer to call both of them as variation of parameter. Okay, how about the second type of example? Those are about non-homogeneous ODEs. Here's a review. Homogeneous equation equal to 0. Non-homogeneous equation equal to some other function. Okay, here's the setting. Let's begin with a non-homogeneous linear ODE with standard form. We're considering the monic case. If you have a leading coefficient here, divide it away and make it into 1. Okay, that's the starting point. Okay, and then let y1 and y2 be a pair of linearly independent solutions of homogeneous equation. And then we are going to set yp as the linear combination. As a matter of fact, we can begin like this. c1y1 plus c2y2. And then we are going to change c1 and c2 around. Of course, I cannot change them around if they are set as constant coefficients. Variation of constant, that doesn't make any sense. That's an oxymoron. So change those into parameters, excuse me, typo. Change them into parameters and then apply the derivative rules and so on. Plug everything back into the original equation and try to identify u1 and u2. And that's going to be my particular solution. But you have two unknowns, u1 and u2, and only one equation. That's not going to cut it. So we need another condition and return to this rather strange equation here. Artificially selected equation. And this one is typically called variation of parameter condition. And that gives you two equations and two unknowns. With some difficulty, you can solve it. Once you do, you're going to get this kind of form. Let's see. Let's expand the font a little bit because there are too many fractions here. So u1 prime is negative of y2f over Wronskian. u2 prime is y1f over Wronskian, and Wronskian determinant is y1 y2 prime, y1 prime y2, or equivalently y2 y1 prime. And that goes to the denominator. And of course, those are u1 prime and u2 prime. In order to get u1 and u2, you have to take the antiderivatives, this integral and that integral. That's your yp. Now, if you add this yp to the general solution of the homogeneous part, then you're going to get the general solution of the non-homogeneous equation. Now, before going over to the proof, let's do at least one example problem and then come back to the proof. How about this problem here? Does everybody recall this? We encountered it in Laplace transform method here, this problem, and then using the Laplace transform method, you're going to get one solution. This one, sine of t over t, but not the other solution. So how do? You can use this reduction of order here, and then you can find y2. That turned out to be cosine of t over t. Okay, these are the solutions of homogeneous equation, and these two are linearly independent. And here's a non-homogeneous equation. Let's find out the solution of the non-homogeneous equation, the general solution of the non-homogeneous equation. So we have to calculate this. And here's the equation. But please note that this is not in the standard form. You see, we have to have monic. The first coefficient, or the leading coefficient, has to be 1. So from here, divide everything by t, then y double prime plus 2 over t y plus y prime. No, this is y prime plus y equals 1 over t. And that is my f of t. Let's put spaces in between. And this is a very typical step that a lot of students miss. You have to make it standard first. And then you're going to plug into this formula. So what is this? Let's see. What is y1? It is sine over t, sine of t over t. So it's going to be this one. Sine of t over t. And then cosine of t over t. And that's cosine of t over t. And that's sine of t over t. And I'm gonna need a little bit bigger font here. Okay, all right. And then how about y2 here? That's cosine of t over t. And what is this f of t? This is 1 over t, so we have times 1 over t, so we get t squared here. Not this one, it's not 1, it's 1 over t. Same thing goes here. This is sine of t over t, and then we are multiplying 1 over t, so this is over t squared. Now how about the denominator? Vronsky and determinant. Well, okay, all right, let's calculate that thing. So we have y1 y2 prime minus y2 y1 prime. So what is y1? It is sine of t over t. And then what's y2? That's cosine of t over t. How about y2 here? Basically it's this one, but I have to take the derivative. And then this one, but I have to take the derivative. How about the derivative? Let's copy and paste this thing, and let's take the derivative. let's see, it's gonna be a quotient rule, so denominator squared. So the derivative of the numerator times the denominator minus numerator times the derivative of denominator, which is 1. So there you go. How about this derivative here? Denominator squared and derivative of the numerator times the denominator times numerator times the derivative of denominator, which is 1. Okay, and further computation, let's see. Putting all these, so multiply sine, so negative t sine squared of t, and as a matter of fact, denominator is t cubed. And then multiply, so this is going to be minus sine of t cosine of t, and then minus t cosine squared of t, and minus minus plus cosine of t sine of t. So what do you get? Use this cancellation, sine cosine, they disappear. Let's copy and paste. So these two cancel out. And then this t cubed, they cancel out. And then sine squared plus cosine squared is 1. So this is negative 1 over t squared. Okay, therefore the denominator here is negative 1 over t squared. Looks like further simplification yields canceling these t squared, and then the antiderivative of cosine, antiderivative of sine. Looks like this is not going to be too challenging a computation once the Vronschian is done. So here you go. Okay, homogeneous solutions are provided. And then here's the standard form, and okay, all right. We're going to find out Vronschian determinant. Negative 1 over t squared. And the numerators are like this, cosine of t over t squared, sine of t over t squared. So the integrals can be calculated like this. T squared, they cancel each other out. We have just cosine and sine. And therefore we have sine and cosine. So we have sine squared plus cosine squared. You're going to get 1 over t. So the particular solution is 1 over t. Hence the general solution is c1y1 plus c2y2 plus particular solution 1 over t, and that's got to be the general solution. Here we go. You can check it using Mathematica, and the right hand side is indeed 1. Okay, here's the entire solution in a single viewing window. Okay, the original equation into the standard form. This is absolutely necessary because we need to find f of t, which I'm highlighting here, highlighting in red here, and highlighting in red over there. Okay, a lot of students make mistake here, try to use this one right away. That's not going to work. And then we have to calculate, let's see, the denominator Wronskian. Okay, here's the Wronskian determinant computation. y1, y2 prime minus y2, y1 prime. And then the numerator, put them together, and then we can do integral computation. We end up with 1 over t. The particular solution is 1 over t. So add them up. We have the general solution of the non-homogeneous equation. This kind of method is a variation of parameter. So it has rather complicated formula and a lot of complicated computation, but they're just computations. They're just formula computation, no big deal. Well, do you have another problem here? Okay, all right. And one solution, t plus 1, the other solution, e to the t power. They are provided. As a matter of fact, when did he encounter these problems? Yeah, I think it came from here. From the Laplace transform problem. Yes, e to the t power, t plus 1. Okay, all right. Those are two linearly independent solutions, y1 and y2. And then we are looking for the particular solution, basically using this, or, excuse me, this is a general solution problem, and this is a particular solution formula. Find it and then add them up, then you get just the solution. Okay, we have two solutions, y1 and y2, and let's set up yp, and let's make it standard first. Divide by t, so we have f of t as t e to the t power. This one is not read, as a matter of fact. It can be misleading here. Divide by t, and this one, this is my f of t. And then we have to calculate this. Well, y1 and y2 are t plus 1 and e to the t power respectively. So we can calculate all those derivatives and put everything into this Wronskian formula. You're going to get t e to the t power. And that's going to be the denominator. So that's going to be the denominator. And then y1 and y2 are given like these. Get all those blue. Increase the font a little bit so that you can see all these. So you can calculate the numerator. y2 times f, y1 times f, you get these. Therefore, we have this kind of integral. Not too bad, you have a lot of cancellations. So easy computation, and then you end up with this. That's your particular solution, yp. So once you have particular solution, then you have c1y1 plus c2y2 plus yp, and here's your general solution. c1y1 plus c2y2 plus particular solution. Here's a checking process. Well, let's see. Is everything in the same viewing window here? Original problem and the standard form, and then yp formula, denominator computation, Wronskian, and the numerator computation, integral computation, eventually yp, and here, general solution, c1y1 plus c2y2 plus yp. Everything is in the same viewing window. All good.